Good afternoon, everyone, and thank you for attending our EMI shielding methods for flex and rigid flex PCB designs webinar. My name is Ed McMahon. I'm the CEO here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. So if you have any questions as we move along, go ahead and enter them into the questions panel that's located on the webinar control panel, and we'll try to get to all of them at the end of the presentation. And if we don't have time to get through all your questions, we'll be sure to reply back to you by email. Along with that, we're going to be recording this webinar like we do all of our webinars and posting both the recording and the slide deck on our website and YouTube channel. So today our presenter is Paul Tomei, who's our product manager for flex and rigid flex circuits. Paul oversees our entire flex and rigid flex product line, where he works with customers on a day-to-day basis for technical support and being involved in every project from the beginning of the design stage just all the way through delivery. You know, his over 24 years of experience, not only in designing and manufacturing, but also troubleshooting, are really invaluable when it comes to flex and rigid flex circuits. And in our company, he's been involved in so many different things. So we're excited to have him presenting today. And without further ado, I'll pass it over to Paul.
Thank you, Ed. Good afternoon, everyone. Thanks again for joining us today. We really appreciate it. Well, the topic of this webinar today is EMI shieldings for flex and rigid flex designs, which is actually a very timely topic from our perspective, as we're having more and more discussions with our customers regarding EMI shielding and how to accomplish it, how to meet their bend and flexibility requirements. So I think it's a very timely webinar. So our agenda today is we're going to do a quick little one-page overview of EMI. We're not going to delve into the rationale or the reasons why EMI shielding is required. We're just going to touch upon it. Our focus is going to be more on how it's implemented into a flex. So we're going to talk about the three main shielding options that are available, utilizing copper layers, utilizing silver epoxy inks, and utilizing specialized EMI shielding films. We're going to go through all of those. We're going to discuss what they are. We'll then go through the pros and cons of each of the three different methodologies. And then we're going to finish off with how those methodologies are applied or implemented at the Gerber design stage. So EMI. EMI, by definition, is a disturbance that's created by an electrical source that affects an electrical circuit by either electromagnetic induction, electrostatic coupling, or conduction. The negative impact of EMI is that it can significantly degrade or prevent the performances of a circuit and stop it from even functioning. Its effects can range from an increase in the error rate that's seen in the signals to a total loss of data. Shielding can be applied at many levels in an assembly. Our discussion is going to be the implementation of shielding at the circuit level. And the primary reason for implementing shielding at the circuit level is it is arguably the most cost-effective location in order to implement it. So the overall costs are reduced when shielding is applied closest to the sensitive circuits. So moving on. So we'll now get into the three different shielding methodologies. So the first one we'll discuss is the implementation of shielding by copper layers. So the construction is very straightforward. Additional copper layers are added external to the shielding layers so that the critical signals are encapsulated on both sides by copper layers. It's essentially the same solution that's used in rigid PCB designs. And the shields, the copper shields, can either be solid, which is generally the preferred solution, or they can be done as cross-hatched planes. Solid plane will provide a higher degree of shielding. cross-hatching is used if flexibility becomes a concern in the design. Copper layers are definitely the required solution for controlled impedance. The other solutions they just don't perform anywhere near as well as solid copper layers. So these additional layers, same as in a rigid board, would interconnect to the ground circuit of the design through via holes. Now in a flex, as compared to a rigid board, it's very common where those shielding layers are stitched together with via holes. You might refer to it as a Faraday cage. Because there's a mechanical bend requirement, you can add those vias in the flex areas, but it will degrade the flexibility of the design. IPC 2223, which is the design standard for flex and rigid flex, does not recommend adding vias in the flexible area because it does degrade flexibility, and it could potentially create a stress concentrator where if the flex is bent extremely tightly, you could induce a crack. So under these circumstances, we strongly recommend to all of our customers that a bend requirement review be performed to ensure that ultimately at the end of the day, the finished parts are reliable and meet the bend requirements. So this graphic here is just a simplified profile view of the construction of a rigid flex. In this case here on the right-hand side, it terminates at what represents a ZIF interconnect. And you can see that layer 3 is a critical signal layer. It's encapsulated on either side by layers 2 and should be 4. The layer numbering is not correct, but it's encapsulated on both sides by the solid shields that we just described. The next methodology is utilizing silver ink. So the construction of silver ink is essentially the screening of a layer of silver epoxy ink on the external surfaces of the cover lay of the flex circuit itself. And then the silver ink is again encapsulated with a second layer of cover lay. The silver ink connects to the ground through selective round openings in the primary cover lay. And the silver ink will then flow down into those openings and both electrically and mechanically attach to the ground net to create so that you don't have a floating shield. And then that silver ink, again, as I mentioned, is encapsulated by the secondary cover lay. There's some added cost to this process. It does add many additional process steps and materials to a design. The silver ink needs to be screened on, needs to be baked. The second cover lay needs to be manufactured and laminated onto the surface of the silver ink. And then all of that's repeated again if shielding is required on both sides of the design. Silver ink is the original alternative shielding method to copper layers prior to the introduction of shielding films, which we'll discuss next. It's been around for a long time, and you can arguably refer to it as a very old school technology. It's been around for longer than I have. So this graphic here is again a cross-sectional representation of a 2-layer flex circuit with silver ink shields applied to both sides. So the silver ink shields above and below, and directly above layer 1 and directly below layer 2 copper, there's a cover lay, and this represents, these areas here represent the openings in the cover lay for which the silver ink material then flows down, interconnects to the ground nets, shorts itself out, and then is encapsulated on both sides by a cover lay on the top and on the bottom. So the third method, and I'm going to preface this by saying that this is by far the most commonly used and popular solution for shielding if in non-controlled impedance designs that we see today. So shielding films were specifically designed for flexible circuits. They were originally, when I first saw them, was when flip phones came out back in the mid-90s. There was a flex circuit that interconnected the upper screen to the lower keypad that had to pass through the hinge mechanism. It was sensitive to EMI and noise, and that's specifically what I recall was what resulted in the development of these films. So the film itself is a 3-layer composite. It consists, the 3 layers are, starting from the bottom up, an electrically conductive adhesive. And then above that is a metallic deposition layer that does the actual bulk of the shielding. And then it is in turn encapsulated with a flexible epoxy in order to insulate the metallic deposition layer. The shielding film connects to ground through selective openings in the primary cover lay, essentially the same method as the silver ink, but due to it having its own built-in insulation layer, there is no need for a secondary cover lay, which gives this methodology a significant advantage. An additional characteristic of the shielding film is that the outer insulation layer is friction resistant. And again, this goes back to that hinge application in flip phones where there is the opportunity for the flex to get galled. So having that slip property, the external surface of the shielding film was a necessity. Shielding films are extremely flexible. You can apply them to a wide variety of situations and designs. So the first construction here, again, a cross-sectional view, is the application of shielding film to both sides of a single layer design. And the shielding film, as you can see in the gray areas, will go down, interconnect to the cover lay, will pass through the cover lay, interconnect to the copper, and then at those copper locations, we'll then have a drilled hole that will allow the underlying shielding film to, when it gets laminated on, extrude up through the polyimide core and make contact to the barrel of the copper and to the underside of the upper layer shielding film. In this construction, this represents a 2-layer, but this could also be a 3 or a 4-layer flex circuit. Again, very similar to that of the silver ink, with the big exception being that there is no additional encapsulating cover lay needed above or below the shielding films. And this last application, and this is an important one because we're seeing this more and more, is shielding in rigid flex designs. Shielding films are easily applied to rigid flex. The shielding film is applied specifically only in the flexible area. It connects to the ground nets of layers 2 and 3 in this example through the openings in the cover lay that we previously discussed. And then a key element here is to ensure that you have a perfect seal where the flex circuits enter and exit from the rigid sections. Standard practice is to apply an epoxy strain relief to ensure that everything's encapsulated, that there's a perfect seal. And again, we're seeing much higher demand for this requirement as of late. So the next section, we're going to talk about the pros and cons of each of the 3 methods. So starting off with copper layers and the pros. Arguably, it is definitely the most effective shielding method that we've got. Copper is a very good shielding material, and applying a solid copper plane basically gives you the highest level of shielding that can be achieved. Another key pro is that it is the required solution for controlled impedance designs. It also is very suitable for shielding in higher density component areas for flex circuits that have components and or connectors. Because it's a copper layer, you can do some really tight ground pours around the surface mount components. Suitable for every single type of design out there. You can use it in all types of flex circuits and all types of rigid flex designs. And it can be extended under flex stiffeners, and that's something that I'll delve into a little bit more once we get to the pros and cons of shielding films. The cons of copper layers. By far the biggest negative elements to copper layers are the impact on cost and flexibility. So flexibility, utilizing copper layers, you're adding extra layers to the flex circuit. And every time you add an extra layer, you're making that flex circuit thicker and stiffer. And adding shielding on both sides increases the thickness of the flex dramatically, decreases its flexibility. You can use a crosshatch plane, which will improve the flexibility to a degree beyond that of a solid copper plane. But there's an argument to be made that it starts to degrade the quality of the shielding. And it's not, while crosshatching does improve flexibility, it tends to be more of an incremental improvement. It's not by any means an order of magnitude. And the second negative element is definitely that of cost. Layer count is a primary cost driver in any type of flex circuit, be it a rigid flex, or a rigid board. Adding more layers is going to increase the cost of the part by a significant amount. Adding copper planes can definitely be a limited application to flex circuits that are greater than 2 layers. Again, this ties back to the significant increase in the thickness and the reduced bend capability. If you're starting off with 2 circuit layers and you need to shield them on both, you're now up to a 4-layer design, again, significantly thicker. There's also a slight element where taking that 2-layer circuit and evolving it into the 4-layer with shielding on both sides, you are going to consume some circuit real estate because you're going to need to have those surface mount features brought up to the surface. And you'll need to add vias in order to do that to access the SMT components. We don't see that as being a big problem in many designs, but we have encountered it where the customer will start running tight for real estate. So moving on to silver ink, pros. It is an effective shielding method. Arguably, an argument can be made that it's not as effective as copper, but it is a tried and proven shielding methodology. It is less costly than adding copper layer shields. It does result in a design that is more flexible. The silver ink as a material itself is more flexible than copper. It can be extended under stiffeners if required. And again, we'll discuss that a little bit more in detail in the next section. It can be added with limitations to higher layer count designs. By that, I mean 2, 3, 4-layer flex. Again, you're adding additional cover layers on both sides and the silver ink. So there is an increase in the thickness of the flex circuit, which again is going to be detrimental to its flexibility and bend capability. And it's definitely the traditional method. This methodology has been used for decades. The cons of silver ink. You are adding a lot of added process steps and materials during the manufacturing process. You need to add at least 1 to 2 silver ink layers. They need to be screened and baked per side. You have to add additional cover layers. As I mentioned earlier, the increase in thickness is going to reduce the bend capability. Definitely not a recommended process or shielding methodology for controlled impedance designs. If you do it, it's going to necessitate increasing the impedance tolerance beyond the traditional plus or minus 10%. In the past, I've seen it having to be spec'd in the plus or minus 15 to 20%. And in some designs, it can be difficult to achieve the required dielectric thickness between the shield, which is now acting as a reference plane, and the underlying signals, because you're using coverlay materials now to try and achieve that thickness. Creates a deeper well. You have to increase the thickness of the coverlays. Creates a deeper hole or well that the ink needs to extrude down into, which can, in some cases, compromise the interconnect. As a material, it is not compatible with that of rigid flex designs. The silver ink is difficult to position with the accuracy that's required in a rigid flex design, specifically where the flex meets the rigid portions. And then that silver ink is going to be subjected to the heat of the lamination process of the rigid areas, which it doesn't tend to do well with. Silver ink also has some very limited applications in and around high density component areas. The ink itself, because it's screened on, has a fairly large manufacturing tolerance. The web thickness that you can maintain, or the smallest line thickness you can maintain with silver ink, is fairly limited. So it's difficult to get it in between surface mount components in most designs. So the last method is shielding films. And the pros of shielding films is, first of all, it's very effective. It's very, very close to that of copper shield layers. It's also by far the most cost-effective and flexible solution. As a material, it's not cheap, but it is so easy to apply and such a straightforward process that what you invest in the additional cost of the material, you recoup very quickly in the ease of manufacturing and the reduction in process steps. It can be used in component areas with some limitations. Again, there are limits as to how wide a web of material can be maintained. It's better than silver ink. As far as flex and rigid flex designs go, the shielding film is suitable for both. There is no problem in using it in a rigid flex. By far, it's the most used solution for non-controlled impedance designs that we see in the industry today. And the primary or the main manufacturer of the film, company that we use extensively, called Tatsuda, has a variety of films available that have different capabilities. They'll be able to handle different coverlay thicknesses. There are different thicknesses. Some of them have some slightly different shielding characteristics. So they have a very broad range of material offerings. So this page here is from the Tatsuda marketing material, and I'm not going to delve into this in too much detail, but it's basically specific information as to the shielding effectiveness, both from electrical field and a magnetic field of the material. Shielding film cons. So as I mentioned before, not recommended for controlled impedance design. I have seen it done, but it did require increasing the controlled impedance tolerance to at least plus or minus 15%. And again, it can be difficult to achieve the required dielectric thickness with the shielding film acting as a reference plane because of the coverlay thickness and the deeper well that the adhesive then has to extrude down into in order to interconnect to the ground layers. It has some limited capabilities in higher density component areas due to the minimum web thickness requirements of the material. If you try to go below what the material can support, those webs will break and cause parts to get scrapped out. one downside, and I've only encountered this twice, is because the material, the shielding material, starts off as a solid sheet. It's essentially the same width as the flex core and coverlay material that we start off with in manufacturing. When you cut it to size and then attach it to the flex, you do expose the shielding material, the metallic shielding material on the periphery of the part. But as I said, 99.99% of the cases, not an issue. I've only had 2 customers come back and express concern that the shield itself might in turn short out to another component within the design, within the assembly, the finished assembly. Now, I alluded to stiffener laminations in both the copper layer and silver ink solutions. Because of the anti-slip, because of the slip properties or the friction resistant properties of the shielding film, attaching a stiffener to that material is a bit of a challenge. The traditional method of laminating stiffeners on under heat and pressure is nowhere near as effective as it is when you're laminating it onto, say, the coverlay of a non-shielded flex circuit. It just doesn't stick as well as it needs to, or as it should. In designs where the shields have to extend underneath the stiffeners, what we'll do is we'll attach them with a PSA. Again, that's an effective methodology. We'll typically use a high bond strength 3M product to achieve that, so it can be done. So shielding methods and how to implement them into your Gerber designs. We'll start off with copper shields, and this is by far the easiest solution to implement. It's essentially a very simple process of just adding 2 additional layers externally on the existing design as copper pores, supported by every single CAD system that's out there. Additional vias are going to be required to route circuits up to the SMT components, which are now going to be present on the external shield layers for them to be accessible from the internal layers. And via stitching in the flex areas, basically to create that Faraday cage scenario, are possible. But we do need to keep in mind that adding those vias is going to limit the flexibility of the design. And as I mentioned previously, IPC 2223C does not recommend it and suggests that you avoid it if at all possible. So side profile construction of a 3-layer flex circuit with shield layers, again, very simple. The design started off as a 1-layer with just the signal layers, then layers 2 and 3 were added as ground poured shields. Silver ink designs, silver ink shields, Gerber design. This is by far the most complex of the 3. And I found over the years that it is not well supported, if at all, by CAD systems. The silver ink layer itself is designed essentially as an additional cover lay, but with some much larger tolerances and parameters. For example, the openings in the silver ink layer need to be oversized by 20 thou in relation to the features in the primary cover lay for PTH or surface mount components. That's driven by the process tolerances and material tolerances of the silver ink and the silver ink application method. Very limited as to your minimum line width. We like to see 50 thou. You can go a little lower than that, but usually you start running into issues where there just isn't enough space between components, SMT features. And you also need to design it with a setback from the part outline, because you don't ever want to have the silver ink exposed along the part edge. You need to have that setback in order for the upper shield cover coat to be able to wrap around and encapsulate the silver ink. So the image beside represents the construction. The bottom layer, this is our circuit. We've got our ground net along the bottom edge of it. Then we apply the first layer of cover coat with the openings for the components at the leading edge. And then along the length of the flex, these are the openings in the cover lay for the silver ink to ground out. We've got the silver ink layer itself, and then we've got the secondary cover lay that gets laminated on top of that. So it can be a little bit of a challenge, especially in today's designs where things are getting much higher density. It definitely becomes more complex trying to design an effective shield with silver ink. As I mentioned, the secondary cover lay is required. Again, now we need to add additional tolerances onto that in order to accommodate the manufacturing process tolerances of the silver ink itself and to ensure that the silver ink becomes fully encapsulated. We mentioned the need for a ground circuit. Virtually all circuits, they're all flex circuit designs that we see do have inherent ground circuits. They do need to be of a minimum trace width though, typically 20 thou or greater, in order to accommodate the openings in the cover lay that the silver ink is going to flow down into in order to interconnect to the ground. Because of these complexities, we often see our customers basically throw their hands up and say, well, we want to use a silver ink shield, but we're not sure how to design it. Can you do it for us? And that's fine. We do that on a regular basis. The customer will give us some information as to where the extents of the shield need to be, and then we'll take a closer look at that. And in most cases, we'll create the Gerber layer design, the Gerber data for the shield and the cover lays on behalf of the customer. The downside of that approach is it is now not part of the CAD database. So the last one is shielding films, and this kind of falls in between that of copper layers and the silver ink methodology. From our perspective, it's a fairly simple Gerber design solution. The shield is essentially treated as a secondary cover lay. We've seen other customers treat it as a mechanical layer. The openings do require an additional oversizing to the primary cover lay. There is a minimum web thickness that needs to be maintained for the material. Again, it accesses the ground net through selective 20 thou openings in the cover lay. In the vast majority of the designs, and the preferred solution is that the shield extends right out to the part outline. That's a preferred solution because when we create the flex circuit, we'll actually laminate the shield across the entire extent of the production panel. And then at the end of the process, when we go back in to cut out the part outline, either laser cutting or punch and die or whatever the solution is, we'll actually cut through the shield, through the cover lays, through the flex core material itself, all in one pass to give you a perfectly lined up solution, perfectly lined up edge on all of the materials for the part outline. As I displayed earlier on, in a rigid flex design, the shielding film is applied only to the flexed areas, and epoxy strain reliefs are then necessary at the transition from the flex to the rigid areas, wherever the shields are applied, in order to create a complete seal in those areas. So in a couple of odd cases where the customer was not able to accommodate having the exposed perimeter of the metallized shielding layer around the perimeter of the part, in both cases, the designs did allow for the shielding film to be, for lack of a better phrase, postage stamped in place. So the shields were created as separate entities. They were undersized slightly from the part outline, and then we positioned them in place and laminated them in place. Now, there can be some limitations to the size and shape of the application. This kind of opens a little bit of Pandora's box, where if you have very, very small shielding areas or very, very intricate shape of shields, having it extend to the part outline eliminates those complexities because we're not worried about trying to create the profile of the shield independent from that of the flex. But if we're trying to postage stamp it in place, sometimes you create a very small and delicate piece of material that then is very difficult to handle and position onto the flex circuit. At the end of the day, it is an added cost to manufacture and position a shield if you're going to try and postage stamp them in place. So I alluded to before that the shields cannot be extended under the stiffeners. So this is a graphic example of that, where the shield will run up to, but not under, the FR4 stiffeners located on the left and right side of this part. Those FR4 stiffeners are there to support either component or connector areas that would exist on layer 1 in this design. Typically, we don't see this being a problem for our customers. In many cases, shielding can be added onto layer 2 in the form of a ground pour, specifically under the FR4 stiffener. The FR4 stiffener itself does provide a degree of shielding. We've done this and we've seen this in many, many, many designs, and I can't recall a customer ever coming back and saying, well, we've got an EMI problem and it's related to the shielding film not being present under the stiffeners. So in summary, with the 3 options available, shielding a flex circuit or the flex areas in a rigid flex is very easily accomplished. Most applications that we see have at least one, if not more, available shielding options that the customer can consider. The preferred shielding solution is going to be dependent upon the design requirements. Big part of that is going to be the flexibility to meet the design-specific minimum bend requirements. It's going to also be significantly dependent upon whether controlled impedance is required. And you also need to be cognizant of the flex area layer count, because adding copper layers is increasing your flex area count, increasing your cost, decreasing your flexibility. All 3 methods are proven to provide sufficient shielding to meet virtually all EMI requirements. I'm hard pressed to think of an application where the customer failed their EMI testing after implementing either one of the 3 solutions. In the industry today, by far the most common method are either copper layers, primarily driven by a controlled impedance requirement, and shielding films for non-controlled impedance applications. And we've definitely seen that the demand for silver ink, and in turn the supply chain for silver ink, is continuing to diminish year over year over year. It is, we rarely see silver ink applications. If we do, they tend to be legacy designs that were designed back in the late 90s, early 2000s, before shielding films started to gain in popularity. On the odd occasion, we'll see a customer developing a new design based on a silver ink shield. And under those circumstances, we'll immediately have the discussion with the customer about EMI, about using an EMI shielding film as opposed to silver ink. And in every single case, the customers agreed with us and we've moved forward with that. And in every single case, the customer's customer's requirements have been met. Thank you for your time today. I'm going to turn it back over to Mr. McMahon. He's got a few more pages to cover, and I'll start taking a look at some of the questions, and we'll be back with some answers to some of the submitted questions. Thank you.
Thanks, Paul. Really quickly, we've got just a quick few things to go over. First of all, for those of you that don't know us very well, we've been making flex and rigid flex circuits for over 20 years and making rigid printed circuit boards for over 60. Along with that, we make many other products for the mil aero, defense, medical, industrial applications that you can see here, all of which were based upon our start in printed circuit boards a long time ago. Next slide, please. One of the things I wanted to point out to everybody is I hope you found this informative. Every time I listen to one of Paul's webinars, I learned something that I've never heard of before. But we have a substantial amount of free online technical resources on our website. Not only do we have all of the webinars we've been doing over the past, I believe it's 7 years now, that have been recorded. We have technical articles that we publish 10 times a year. We've got design guides that are updated every 2 years and different ebooks for everybody to see, along with our blog where we usually publish something technical once a week. And Paul has a page on his own as well that you can go and look at all the different flex and rigid flex stuff. So we urge you to check out on the free online technical resources. Again, they're there for you. We have the in-house engineering folks like Paul for every one of our product lines. So if you have more questions like that or questions on any of the products, we have the people there that can help you with whatever your design question may be. Next slide, please. And lastly, before I turn it over to Paul, we not only manufacture our rigid and rigid flex printed circuit boards in Asia at many different locations, but we own a factory in Dallas that's got 25 years of PCB experience that has been doing flex and rigid flex boards for many years, and along with some very high-tech rigid parts. So we can do both. Many times companies can do a lot of stuff in Asia, especially with flex and rigid flex, with how new the technology is. Well, we can do both. And we've invested pretty heavily in the equipment that we need to do real high-end technology at our facility in Dallas. And we have the people down there from a technology perspective that can help on any designs. We work with a lot of different tier 1 defense contractors on ITAR defense stuff, along with different medical folks, along with doing some pretty high-tech stuff on quick turns and prototypes as well. So with that being said, I'll kind of turn it over to Paul because there was a lot of questions and I'm sure we're not going to get to all today.
Thank you, Ed. So yes, we've got a lot of questions. We picked out 5 that we're going to answer because we don't want to take up all of your day. And as Ed mentioned earlier, we will be answering each and every question. We'll be getting back to you through email, and we appreciate you submitting your questions. So the first question we have here is whether there are other shielding materials available. And this actually ties in with discussions that we've had with customers as of very recently, specifically copper or aluminum foils, conductive tapes, sputtered metals. And the simple answer for that is yes, but not for flex and rigid flex applications. They're just not part of the industry's demand for flex and rigid flex. Sputtering metals is a very unique process. And at the end of the day, we just haven't seen any application that is ultimately demanded that can't be solved by the 3 methodologies that we discussed today. Second question, and again, this is a fairly common one, is can a shielding film or silver ink be used for current carrying requirements? The most common being a ground return circuit. And per the materials manufacturer's specifications, the answer to that is no, it should not be used as a ground return. The material itself was never designed and or rated to carry any current. And you need to keep in mind that the electrical connection between the shielding film is an electrically conductive adhesive. It is not a soldered or copper plated connection. So that can create some issues. Third question is regarding ferrites. Can ferrites be used on flexible circuits? And the answer is, in general, yes. Not overly common, but I have in prior history manufactured flexible circuits that ultimately have a ferrite inserted onto them. Some of the concerns, it may create some assembly issues, because in most cases the flex will need to be threaded through and or wrapped around the ferrite. And you'll need to do this first before any connectors or components are attached, because typically the opening in the ferrite isn't going to be large enough to accommodate anything more than the thickness of the flex. So under those circumstances, it might force the flex to be hand assembled, which is always, in a small quantity run. It can be considered. In larger volumes, definitely not the preferred solution. In general, we find that adding a ferrite to a flex circuit works best if the flex is a ZIF connector design, where there's no additional connector required. So you'll have at least a ZIF contact fingers on one end of the flex circuit, which will allow you to thread it through the ferrite without compromising the assembly process. Fourth question kind of goes back to the controlled impedance design question and why silver ink and shielding films are not recommended. As I touched upon before, one of the biggest challenges is achieving the correct dielectric thickness between the signal layer and the shield layer, which is now also required to act as a reference plane. You need to accomplish that thickness by the cover lay. Cover lays are typically on the thinner side. 1/2 mil, 1 mil thickness is the two most common thicknesses for cover lay, which is not going to be enough is not going to be thick enough for your dielectric thickness to hit your impedance values. You can laminate multiple cover lays to get to that thickness, but you're now adding cost and thickness again. But the biggest concern then becomes, now with this added thickness of cover lay, either the silver ink or the shielding adhesive needs to penetrate down into this cavity that you've created in order to access the ground net. And the adhesive is only so thick, and it can only accommodate a certain amount of thickness in the cover lay before it just can't make proper connection to the ground. And as I also mentioned, because of the characteristics of the material, and the inconsistencies of it in relation to copper, your controlled impedance tolerance is going to increase, in some cases beyond what the design is going to allow you to utilize. You're going to be easily up into the plus or minus 15 to 20% range now on your controlled impedance. And the last question I got before I will sign off for the day is, and this is again a very, very common question that a lot of customers will come to us. We'll get involved at an early design stage, in many cases a conceptual one. And at that point in time, the customer is unsure as to what their shielding requirements may or may not be. They're either unknown or they're yet to be defined. And what we do in the majority of cases at the prototype stage, as part of one order, we'll supply parts with and without shielding films under one part number and under only one tooling charge. And that'll give our customers the opportunity to evaluate the designs both with and without the shieldings, and then make an informed decision moving forward into production as to whether or not shielding is specifically required for their design. And with that, I'm going to close off. Again, thank you very much for your time today. We greatly appreciate it. Any questions, just submit them. We will answer any and all questions. And again, thank you very much and have yourselves a great day.